Good morning, student. Today we are going to see the fundamentals of limit system for the subject MEE 2001 Machine Drawing. My name is Arogya Selvakumar, Associate Professor, School of Mechanical and Building Sciences, VIT University, Chennai. First of all, I would like to start with the introduction. The introduction deals with the limit system, why we need limit system, and what are the terms used in the limit system. The manufacture of interchangeable parts require precision. Most of you will know what is precision, but for others, the precision is the degree of accuracy to ensure the functioning of a part as intended. However, experience shows that it is impossible to make parts economically to the exact dimensions. This may be due to inaccuracies of machines and tools, inaccuracies in setting the work to the tool, error in measurement, etc. The workman therefore has to be given some allowable margin so that he can produce a part, the dimensions of which will lie between two acceptable limits, a maximum and a minimum. So all the parts cannot be made as per the perfect size. It will have a higher limit or a lower limit. For example, if you want to produce a shaft for exactly 50 mm, present based on the manufacturing process available, so based on the experience, it is impossible to make exactly 50 mm. So it will have maybe a maximum of 50.01 mm or a minimum of 49.99 mm. This is an example. The system in which a variation is accepted is called the limit system, and the allowable deviations are called tolerances. The relationships between the mating parts are called fits. The study of limits, tolerances, and fits is a must for technologists involved in production. The same must be reflected on production drawing for guiding the craftsman on the shop floor. As discussed in the class, the machine component drawing will have only the dimensions of a particular component without fits, tolerances, and limits. So if these three parameters, that is limits, tolerances, and fits, are included in the machine component drawing, then it is called as production drawing. So now we will see the terms used in the limit system. Before that, I want to explain the diagram illustrating basic size, deviations, and tolerances. So if you see the diagram, so you're having a shaft and a hole, and the shaft is having a basic size, maximum diameter, minimum diameter, upper deviation, lower deviation, and tolerance. And the very important zero line or line of zero deviation. Similarly, hole is having the same parameters, which will be useful for you to know about limits, fits, and tolerances. So from the figure, the two limit dimensions, that is shaft, are deviating in the negative direction with respect to the basic size, and the hole in the positive direction. The line corresponding to the basic size is called the zero line or line of zero deviation. So now we will see the terms used in the limit system. Number one is tolerance. So based on the figure, tolerance is the permissible variation of a size is called tolerance. That means maximum and minimum. It is the difference between the maximum and minimum permissible limits of the given size. So if you see the diagram in the shaft side, you are having a maximum diameter and the minimum diameter. So the difference between the maximum diameter and minimum diameter is called tolerance. Similarly, in the hole side, the maximum diameter of the hole and the minimum diameter of the hole, the difference between these two is called as tolerance. So you can see in the figure tolerance. Similarly, the tolerance of the hole. If the variation is provided on one side of the basic size, that is, for example, the shaft diameter is 30 mm, the tolerance is provided plus only in positive direction and negative direction is 0, then it is called as unilateral tolerance. Similarly, the tolerance may be only in negative direction, not in the positive direction, also called as unilateral tolerance. To understand better, see the example of unilateral tolerance 25 plus 0.02 plus 0.01, and see the last one 25 plus 0.0 and 25 minus 0.02. So these are the examples of unilateral tolerance. So the variation is provided on one side of the basic size. The next term is if the variation is provided both sides of the basic size, it is known as bilateral tolerance. That is, example 25 plus 0.02, 25 minus 0.01. So you can see the example 25 plus or minus 0.02 and 25 plus 0.02 minus 0.01. The plus 0.02 and plus 0.01 and plus 0.02 minus 0.01, all these things are nothing but the tolerance values. The next term is limits. The two extreme permissible sizes between which the actual size is contained are called limits. The maximum size is called the upper limit and the minimum size is called the lower limit. Next one is deviation. It is the algebraic difference between a size, that is actual, maximum, etc., and the corresponding basic size. So if you see the diagram, so you can understand the upper limit and the lower limit. Similarly, you can understand the basic size, actual and maximum sizes of the shaft and hole. So for better understanding, I am mentioning the basic size and the zero line or line of zero deviation. Based on this one only, you will get a maximum size, minimum size, actual, everything. The next term is actual deviation. Again, I want to explain the same thing. It is the algebraic difference between the actual size and the corresponding size. So from the figure you can understand what is basic size. The next one is upper deviation. So based on the figure you can say that upper deviation, which is coming above the limit of maximum diameter of the hole. Similarly, it is coming above the limit of your basic size in the hole area. It is the algebraic difference between the maximum limit of the size and the corresponding basic size. Upper deviation. The next one is lower deviation. It is the algebraic difference between the minimum limit of the size and the corresponding basic size. So based on the figure I can explain that the lower deviation of the hole is coming between the minimum diameter and the basic size, and in the shaft it is coming minimum diameter of the shaft and the zero line or line of zero deviation. So you can see in the figure for the shaft. Next one is allowance. It is the dimensional difference between the maximum material limits of the mating parts intentionally provided to obtain the desired class of fit. If the allowance is positive, it will result in minimum clearance between the mating parts and if the allowance is negative, it will result in maximum interference. So better understanding the allowance, we will have some problems. Here I want to explain with the zero line or line of zero deviation, that is nothing but basic size. So based on this one only, the dimensional difference between the maximum material limits of the matting parts can be achieved. So next important one is basic size. This term says it is determined solely from design calculations. If the strength and stiffness requirements need a 50 mm diameter shaft, then 50 mm is the basic shaft size. If it has to fit into a hole, then 50 mm is the basic size of the hole. So the two things are clearly mentioned in the diagram. See the basic size, which will align with the zero line or line of zero deviation. If you want 50 mm diameter shaft, the basic size should be 50. If you want a 50 mm diameter of the hole, the same basic size will be 50. Next term is design size. It is the size from which the limits of size are derived by the application of tolerances. If there is no allowance, the design size is the same as the basic size. If there is no allowance, the design size is same as the basic size. If an allowance of 0.05 mm for clearance is applied, try to understand the word clearance is applied, say to a shaft of 50 mm diameter, then its design size is 50, that is the maximum value of the basic size. You have to subtract that value with the clearance value 0.05 mm, then finally your design size will be 49.95. So design size is nothing but the actual size required subtracted with the allowance limit. A tolerance is then applied to this dimensions. So again I want to explain about in basic size in the figure. So basic size is 50, but we are giving a clearance of 0.05 mm. Actual size means it is the size obtained after manufacture, that is after including tolerance apart from the design size. Next important thing is tolerances. The great care and judgment must be exercised in deciding the tolerances which may be applied on various dimensions of a component. If tolerances are to be minimum, that is, if the accuracy requirements are severe, the cost of production increases. In fact, the actual specified tolerances dictate the method of manufacture. Hence, maximum possible tolerances must be recommended wherever possible. So the graphical illustration of tolerance zones. So you can see the figure. Holes, it is having A2, ZC, that is basic size up to that, and you are having a shaft which is having a basic size from small a to ZC. So fundamental deviations in the left side, negative and positive is the EI is the deviation, and EI is the deviation for the holes, and ES, that lowercase letter, is the deviation for the shaft. EI capital letter, EI small letter. The capital letters are for holes and the small letters for shaft. So ES capital letter for holes and the ES lowercase letters for shaft. So these are the graphical illustration of tolerance zones. So next important thing is fundamental tolerance. The tolerance is denoted by two symbols, a letter symbol and a number symbol, called the grade. The fundamental tolerance is a function of the nominal size and its unit is given by the empirical relation, that is standard tolerance unit, I equal to 0.45 and the cubic root of d plus 0.01 d. D is nothing but the mean diameter of the shaft. So the relative magnitude of tolerances for grade 5 to 16 in terms of tolerance unit I for sizes up to 500 mm is given in the table 1. Grade and tolerant values. So IT5 means the tolerance values is 7i. So I can be calculated based on the empirical relation if you know the mean diameter value. Table 2 explains or gives fundamental tolerance of grades 0, 1, 0 and 1 to 16 values of tolerance in microns. 1 micron is equal to 0.001 mm. So tolerance grades are given, diameter steps in mm are given. So you can see from 3 to 500 mm you are having the various steps in the diameter. Similarly, tolerant grades are 0, 1, 0, 1 to 16. So table 3 again it is explains the values of fundamental deviations for shafts of types A to K. So now it's a letter. Our sizes up to 500 mm is given. So fundamental deviations are in microns, diameter steps in mm. So here they have given the range from 3 to 180 mm. So upper deviation ES, that is as I told you shaft, and lower deviation EI, both the things are given. The lowercase letter A to K is also given. So the same table continues up to 500 mm. So the next one is the fundamental deviations for shafts of types M to ZC, the next level of the letters. So here also it is starting from the Z3 and ends in 500 mm. So similarly, fundamental deviations for holes of types A to N for size up to 500 mm is given in the table. So you can see the lower deviation is in the capital letter EI and the upper deviations are given in ES. Okay, these are the symbols related to the deviations. So A to N is mentioned in this table. Similarly, up to 500 mm is given. So the next one is P to ZC. These are tolerance grades as I told you is given from 3 to 500 mm. The very important table 5. This table give you the formula for fundamental deviation for shafts up to 500 mm. So upper deviation ES, lower deviation EI is given. Shaft designation is given. A2, J8 is given. So some of them are having formula in microns for D in mm, and that is D is the mean diameter. Shaft designation and in microns for D in mm. So for upper deviation and lower deviation it is given. For all the grades it is given. So based on these tables we are going to calculate some problems for the fundamental tolerance. So the problem 1, example, calculate the fundamental tolerance for a shaft of 100 mm and grade 7. So in this problem they have given the shaft diameter is 100 mm and the grade is 7. They are asking you to calculate the fundamental tolerance. So we are having table 1 to 5 for that can be used to calculate the fundamental tolerance of a shaft and a hole. So the shaft size is 100 is given, but based on our table 2, so if you are looking at the table 2, fundamental tolerance of grade 0, 1, 0 and 1 to 16. So you can see the diameter steps in mm. So we are not having for the exact shaft size 100 mm. Instead of that we are having the diameter ranges between 80 to 120 mm. So the 100 mm is lying between 80 to 120. So we have to take a geometrical mean and it can be calculated by D is equal to square root of the product of the two shaft diameter ranges 18 to 120. So if you are calculating you will get 98 mm Then the tolerance unit, as I said earlier, you can calculate based on the empirical relation. I is equal to 0.45 into cubic root of d plus 0.01001 d. The d is nothing but you have to substitute the mean diameter, not 100 mm. That is, I am saying 98 mm, not 100 mm. So once you are substituting, you will get the value I, that is tolerance unit. I is equal to 2.172 microns. So try to understand the value, you will get it in terms of microns. So for grade 7, as per the table 1, so I want to show you the table 1. So this is the table 1. So for the grade 7, if you see the table, so you will come to know IT7, they have given the tolerance value is 16I. So already we calculated the tolerance unit I is equal to 2.172 microns. So if you are multiplying that value 16 times, you will get the actual value of the fundamental tolerance, 35 microns. So when you are working in problems, you have to know all the tables and the standard procedure how to calculate the fundamental tolerance. So for this problem, the value is 35 microns. Second problem, calculate the fundamental deviations for the shaft size 40 m6. So this is fundamental deviations. So shaft size is given 40 and the letter is given as m6. So from table 5, it's like I said earlier, take the table 5 and see the formula which can be used for m. So m is here, you can see. So m, if you want to calculate the fundamental deviation, the formula m is equal to plus IT7 minus IT6. It is given in the table 5. So the lower deviation EI for the shaft m, the same formula IT7 minus IT6. So from the table 2, so now you have to go the previous procedure. So they have given the shaft size is 40, but you have to go to the table 2 and you have to see the standard size of the shaft, but it is in between now. So you can see that it is not exactly 40, so it is in between 30 and 50. So take the range 30 and 50 as the shaft diameter and calculate the mean diameter as like the previous problem. So you will get 38.73 mm. Then you calculate tolerance unit I as like earlier problem. I is equal to 0.45 and D you have to substitute the mean diameter and you will get the value I is equal to 1.58 microns. So once you got, again you go to the tolerance grade 7 from the table 1, that is you will get the same thing. IT7 is equal to 16I. So see here 16I is equal to 16 into 1.58 is equal to 25 microns. So now based on the table 1, you should calculate grade 6 also, that is 10I. So once you are calculating, you will get 16 microns. So now based on the table 5, IT plus, you have to know the formula as I said earlier, plus IT7 minus IT6. So 25 is IT7 value, minus 16 is IT6 value, so that is equal to 9 microns. Okay. So this is based on the table 5 we have calculated. So apart from that, we can calculate the fundamental deviations directly from the table also. How? So go to the table 3 and see the letter M. Okay, so you know the shaft range, there is nothing but 40. So just you see that the range is given 40 and this is the letter M and you see this is the tolerance value. So based on the formula the value is 9 microns and based on the table also the value is 9 microns. So again I will explain. Based on the table 5, we calculated the fundamental deviations of the shaft for the diameter 40 m6. So again I am explaining here how to calculate or how to get it from the table. Table 3 you go select M. See the 40 to 50 mm, it is there clearly 9 mm. So you can go through the table 5 formulae, and the same thing you can directly refer from table 3. So the fundamental deviations for holes are derived from the formula corresponding to the shafts with the following modifications. As a general rule, all the deviations for the types of holes mentioned in the following 2 and 3 are identical with the shaft deviation of the same symbol, letter and grade, but disposed on the other side of the zero line. For example, the lower deviation EI for the hole is equal to the upper deviation ES of the shaft of the same letter symbol but of opposite sign. So the earlier problems we have seen based on the shaft. Now if you want to calculate the fundamental deviation for holes, we can refer the same table 5, but instead of taking it in the positive, you can take it as a opposite sign. That's only given as a general rule for calculating the deviations of the hole. Again I will explain. As a general rule, all the deviations for the types of holes mentioned in second and 2, that is after this I am going to explain, are identical with the shaft deviation of the same symbol, letter and grade, but disposed on the other side of the zero line. For example, the lower deviation EI for the hole is equal to the upper deviation ES of the shaft of the same letter symbol but of opposite sign. So anyway, if you are not getting it clear, when we are doing some problems, you will understand much better. For the holes of size above 3 mm and of type N and of grade 9 and above, the upper deviation ES is 0. So now you can understand when we are talking about hole, all the letters, deviation letters and the grades will come in uppercase letters. For the holes of size above 3 mm of types J, K, M and N of grades up to and inclusive of 8, and for the types P to ZC of grades up to and inclusive of 7, the upper deviation ES is equal to the lower deviation EI of the shaft of same letter symbol but one grade finer, less in number, and of opposite sign, increased by the difference between the tolerances of the two grades in question. So now we will solve fundamental deviations for the whole problem. So here they have given 40 D9. So as I told you, uppercase letter is for whole. So even if they did not give fundamental deviations for the whole, you have to understand that it is the given is whole size. So based on the formula we will derive now from table 5. The deviation for holes also can be obtained as like the general rules mentioned. See here table 5. This is actually given for the shaft. Based on the general rule, what we understood is the same designation, that is A, B, C, D, E, we can take it in terms of uppercase letters, and instead of the value, if it is in positive we have to take it in negative, if it is in negative we have to take it in a positive. So here you can see that the lower deviation EI for the whole D is given by, so this is actually D, actual formula is given for the shaft, but we are taking for the whole. So the formula is given as D is equal to, okay, I am saying about the upper deviation, minus 16D 0.44. So when we are taking for shaft, we have to take the direct formula, but now we are going to calculate for holes the fundamental deviations for the hole. So we have to change this formula to EI, that is the lower deviations is equal to plus 16 capital D into 0.44. Actually don't forget to put the closure bracket of D, then you will have some issues. So now this is nothing but explained in the general rule. You can use the same table but you can change the opposite sign of for the values, so automatically it will become as a whole deviations. So now you can substitute. So you know D how to calculate. So as I told you, it's a 40. You have to go to the table number 2 and you have to see the standard dimensions and you have to calculate. So the standard diameter is given is 30 to 50, but here they ask for 40, so you have to calculate the mean diameter, that is 38.73. Then you have to come for the fundamental deviations of A to N. Now this is whole. See, the range is given as 30 to 40. The letter is given as D. So what is the value is coming? You can directly take it from that 80. So this is one way. So see here, both the things are tallies. So you can calculate from the formula. The same time you can calculate from the table also. So if you are calculating based on this EI 16D 0.44, you will get the value is 80. Similarly, you can come to the table 4 and you can see the diameter, and you can go to the D. It's a letter is given and the value is 80 mm. Okay. So EI is equal to 80 microns based on the formula and also based on the table. So next important thing is fits. The relation between two mating parts is known as a fit, depending upon the actual limits of the hole or shaft sizes. Fits may be classified as clearance fit, transition fit and interference fit. Already explained in the class. Again I want to recollect all those fundamentals so that will give you a clear idea about fits. The first one is clearance fit. It is a fit that gives a clearance between the two mating parts. So first one is minimum clearance. In that, it is the difference between the minimum size of the hole and the maximum size of the shaft in a clearance fit. So try to understand minimum size of the hole and the maximum size of the shaft. So for better understanding, I have taken an example. See here, clearance fit. So whatever explained in the minimum clearance, I am going to show you. See, it is the difference between minimum size of the hole 29.95 and the maximum size of the shaft, that is 29.90, and the maximum clearance is, it is the difference between the maximum size of the hole and the minimum size of the shaft in a clearance or transition fit. See here, maximum diameter of hole 30 and minimum diameter of the shaft 29.85. So when they are asking you to calculate what is the minimum and maximum clearance, so you have to follow this steps to calculate the clearances. So the fit between the shaft and hole for the given diagram is a clearance fit that permits a minimum clearance. See that 29.95 is nothing but minimum size of the hole minus 29.90 is nothing but maximum size of the shaft. So when you are calculate the difference between the minimum size of the hole and the maximum size of the shaft, you are getting 0.05 mm. I am saying about this 29.95 and 29.90. You will get 0.05 mm. Similarly, the maximum clearance is coming plus 0.15. How to calculate? You know that it is nothing but the difference between the maximum size of the hole 30 and the minimum size of the shaft 29.85. So when you are calculating these two things, if it is coming in a positive value, then obviously it is a clearance fit. So next one is interference fit. If the difference between the hole and shaft sizes is negative before assembly, an interference fit is obtained. So it is the magnitude of the difference between the maximum size of the hole and the minimum size of the shaft in an interference fit before assembly. See the diagram. So this shows the interference fit. Again I am going to explain the terms. Maximum diameter of the hole, the value is minimum diameter of the shaft 30.30, and the maximum diameter of the hole is 30.25. It is the magnitude of the difference between the minimum size of the hole and the maximum size of the shaft in an interference or a transition fit before assembly. See here, this is the minimum size of the hole, maximum size of the shaft. So the value is 30.15 minimum size of the hole and 30.40 is maximum size of shaft. So when you are calculating the differences, the shaft in the figure is larger than the hole, so it requires a press fit which has an effect similar to welding of two parts. The value of minimum interference, so you have to use the word clearly when you are calculating the clearance fit. The word should be minimum clearance. When you are calculating the interference, it should be minimum interference. So when you are calculating the minimum interference, you can see that maximum diameter of the hole is 30.25 and the minimum diameter of the shaft is 30.30. So when you are calculating, you are getting the value of 0.05 mm. So the next one is you are calculating the maximum interference. So you can know that minimum size of the hole is 30.15 and the maximum size of the shaft is 30.40. You can see that. So you are getting minus 0.25 mm. So these kind of fits are known as interference fit. So the last one is transition fit. This fit may result in either an interference or a clearance depending upon the actual values of the tolerance of individual parts. So here it shows, the diagram shows the transition fit. The shaft in the figure 1, okay, may be either smaller or larger than the hole. Try to understand the word. The shaft may be either smaller or larger than the hole and still be within the prescribed tolerances, whatever values they have given. It results in a clearance fit when shaft diameter is 29.95 and hole diameter is 30.05. You are getting 0.10 mm. See here, maximum diameter of the hole is 30.05 and minimum diameter of the shaft is 29.95. Similarly, it results in an interference fit when shaft diameter is 30. You can see the shaft diameter is 30 and hole diameter is 29.95. You can see that 29.95. So when you are doing it, you are getting a minus 0.05. So it is having both the clearance and also interference. So when you are having a fit which is having both clearance fit and interference fit for a same value of shaft and hole, okay, then the fit is called as transition fit. So now we will see some conventional representation of three classes of fits. See here, first one is clearance, second one is transition and interference fit. The line is nothing but the basic size. See that the first one, clearance fit, so there is the line. I said that the basic size or zero line of deviations. See that shaft which is coming the below the value, that is the shaft is smaller than the hole, so then it is known as clearance fit. Okay, you are having a clearance, maximum and minimum clearance. The next one is again the same basic size and you are having all the shaft, either it can be a clearance or an interference, then it is coming transition fit. The last one is interference fit. You can see that basic value, you can see that shaft values are always greater than the hole, so obviously it is a press fit, otherwise it is known as interference fit. So based on the limit dimensions of the three classes of fits, two systems are in use, that is the hole basis system and soft basis system. Already we have discussed in the class. So the hole basis system, in the system the size of the shaft is obtained by subtracting the allowance from the basic size of the hole. This gives the design size of the shaft. tolerance are then applied to each part separately. In this system, the lower deviation of the hole is 0. The letter symbol for this situation is H. The hole basis system is preferred in most cases since standard tools like drills, reamers, broaches, etc. are used for making a hole. Next one is shaft basis system. In this system, the size of the hole is obtained by adding the allowance to the basic size of the shaft. This gives the design size for the hole. Tolerance are then applied to each part. In this system, the upper deviation of the shaft is 0. The letter symbol for this situation is H. So you have to know the important thing is for hole basis system, the lower deviation of the hole is 0. For the shaft basis system, the upper deviation of the shaft is 0. So the following figure shows the representation of the hole basis and the shaft basis systems schematically for better understanding. So you can see that the left side examples taken from shaft basis system, and the right side you can see that examples taken from hole basis system. So you can understand that the lower limit and the upper limit, as like earlier what I said. So this is a very important thing. Lower deviation of the hole is 0. In the shaft basis system, upper deviation of the shaft is 0. So now you can understand in this figure. So upper deviation of the shaft is 0. In the hole 6, lower deviation of the hole is 0. So problems. So we'll see simple problems in the fit. A spindle slides freely in a bush. The basic size of the fit is 15 to 10 power minus 3 meter. It is given in meter. If the tolerance quoted are plus 62, 0, it is in microns for the holes, and minus 80, minus 180 for the shaft. So they have given hole and shaft. Find the upper limit and lower limit of the shaft and the minimum clearance. So they said clearly it's a clearance fit. So solution, first you take tolerance are given in units of 1000 of millimeter, you know that. So the upper limit of the hole will be 50.062. So just add the basic size 50 plus say 62 into 10 power minus 3, you will get 50.062 mm, and lower limit for the hole is the same as the basic size, so it is 0 only given, so the basic size is 50.000 mm. The next one is you have to calculate for the shaft. The shaft upper limit they are given that minus 80, and so the basic size is 50, so 50.000 minus 0.080. So here we have given in terms of meter, it's 49.92 millimeter, otherwise 49.92 into 10 power minus 3 meter. Similarly, the lower limit 50 minus 0.180, so you will get 49.82 mm or 49.82 into 10 power minus 3 meter. So the minimum clearance or allowance, as like earlier we said, so 50 minus 49.92, so you will get 8 into 10 power minus 5 mm. This is the minimum clearance or allowance. So allowance is nothing but, as like earlier said, the upper limit and lower limit of the shaft should be considered with the basic size. The minimum clearance or allowances 50 is the basic size minus 49.92. The shaft upper limit is taken and you got the allowances 8 into 10 power minus 5 mm. The next problem is a double pin is required to be inserted in a base. For this application H7 fit for hole and P6 fit for the shaft are chosen. The tolerance quoted are plus 25, 0 for the hole, and plus 42 and 26 for the shaft. Find the upper and lower limits of the hole and also double pin and the maximum interference. So clearly they said interference between double pin and the hole. Basic size is given as same 50 mm. So solution, the upper limit for the hole, you have to simply add it 50 plus 0.025, so you will get 50.025 mm. The lower limit for the hole, similarly 50, they have given 0, so you got it. The next one is the upper limit for double pin, 50 plus 0.042, so you will get 50.042 mm. Next one is the lower limit for double pen will be 50 plus 0.026. So when you are calculating the upper limit for double pen, the value is 50.026 mm. So now when you are calculating the maximum interference between double pin and the hole is, you can see that the value is 50.042 is the upper limit of the double pin minus the basic size 50, so you are getting 42 into 10 power minus 6 meter, otherwise 0.042 millimeter. So this is the way you have to calculate the maximum interference between double pin and the hole. The last problem, for the following hole and shaft assembly, find shaft tolerance, hole tolerance, and state whether the type of fit is. So they have asked you to calculate shaft tolerance, hole tolerance, and state whether the type of fit is. So hole is given 30, so plus 0.05 the value. One is like unilateral tolerance, another one is like bilateral tolerance. Shaft is 30 minus 0.02 and 0.05. So solution, first hole high limit, you know that you can simply add it 30.05 mm, low limit 30, and tolerance 0.05 mm is equal to 5 into 10 power minus 5 meter. So you can mention in mm also. So similarly, shaft high limit 30 minus 0.02, so 29.98 mm. Low limit 30 minus 0.05, so it is 29.95 mm. So tolerance value is, you know, 29.98 minus 29.95, so 0.03 mm or 3 into 10 power minus 5 mm. So now, if we select a high limit of hole and high limit of shaft, then allowance 30.05 minus 29.98, so 0.07 mm. If we choose low limit of hole and high limit of shaft, so low limit of hole is, you know that it is 30, and high limit of shaft is, you know that 29.98. So again you can see 0.02 mm you are getting. So obviously it is giving a clearance, so it's a clearance fit. So you have to calculate all the possibility of getting the limit system. Okay, what kind of limit? So maximum hole value and minimum hole limit value. Similarly, minimum shaft limit value and maximum hole limit value. Everything you have to put, and you have to find which kind of fit it is showing. So this problem comes under clearance fit. So thank you very much. If any queries, email me. Thank you.